Sound can produce tandem waves very much like other wave sources produce waves on strings and rods and etc. Now, standard sound waves in pipes are very analogous to standard transverse waves on strings. We talk usually of two categories of pipes: those that are open at both ends and those that are open in one end and closed in one end. Very much like waves on strings, we talked then of fixed ends and free ends. In this case, an open end must be a pressure node, and we'll see that. We'll talk more of that in a little bit, which is equivalent to a displacement antinode. Okay, that's the open end. The closed end must be a pressure antinode and a displacement node. And like for other waves, the node-to-node distance is lambda over 2. Let's look at an example. Okay, here we have a simulation that's going to show us how a pipe is going to oscillate with two ends open. This end is open and this end is open. The dots that you see here are air molecules. The red curve here is going to represent the displacement of those air molecules. Remember, this is a longitudinal wave, so the air molecules are going to oscillate back and forth in position. A zero displacement means that the air molecule is not going to move much. A large displacement, it means it's going to oscillate back and forth with a large amplitude. In addition to the displacement, we can measure the pressure, and we measure it two different ways here. We have this cyan curve that represents the pressure. A zero here represents zero pressure. This is maximum pressure. We don't have the units here, but that's the idea. In addition to this curve here, we have this color code. Notice here the legend for the color code. Black represents a maximum amplitude. Here it's normalized to -1. Blue, very clear blue, is a maximum amplitude of +1, normalized amplitude of +1. And here is the zero amplitude, somewhere in between. Okay, so now here, this looks very much like what we see in the zero, and this looks very much like what we see in the zero. Okay, let's play the simulation. Okay, so you notice here the air molecules are oscillating in place. The pressure here is remaining at the same zero value, but here the pressure is increasing from a minimum to a maximum. However, if you pay attention to the air molecules there, here the air molecules don't move much, and that's the displacement we see here. But here, if you pay attention towards the open ends, the air molecules are moving with quite an amplitude. So this is the fundamental frequency for a pipe that's open at both ends. So we have antinodes for the displacement, the red curve, and a node in the middle. So we have antinodes at the open ends and a node in the middle. If we look at the pressure instead, we have nodes at the open ends. See, this is the cyan curve. Nodes at both ends, and then an antinode in the middle. This is the first mode. And anyway, to see it as a standing wave, I'm going to speed it up here. Okay. That's the good thing about simulations. We can see things like this. That's the fundamental frequency. Now, if I go to the first harmonic, let me go back here. Look at the frequency here. It's 165 Hertz. At the first harmonic, we have double the frequency, 330 Hertz. Again, I have a pressure node here, a pressure node in the middle, and a pressure node at the other open end. However, for displacement, I have a node here and a node here. An antinode at both open ends. If I go for the third harmonic, that's 3 times the fundamental frequency, we add another node in the middle for the displacement function, for the red curve. So we have 1, 2, 3 nodes. Again, antinodes at the open ends for the red curve, but nodes at the open ends for the pressure curve. This is in summary what we have seen. So you notice here at the fundamental frequency, we are looking here at the pressure representation at the red curve. Here the pressure is the red curve, it's not the same color code as the simulation. So you see here the red curve, we have a node at both open ends and an antinode in the middle. That's my fundamental frequency. And then at the first harmonic, this is what we have. At the second harmonic, mod do, third harmonic, fourth and fifth. We can see both of them here. The pressure segment in red and the cyan, that's the displacement of the air molecules. The way we analyze this is very much like we did it for waves on a string. So this is my fundamental frequency, first harmonic, second harmonic, third, etc. The distance between the nodes is lambda over 2, so if I measure the length of the pipe, I can get from there lambda. The harmonics are related to the fundamental frequency through this simple expression. The nth harmonic is equal to n times the fundamental frequency, or the first harmonic. The wavelength for a pipe that's open at both ends is going to be 2L, L being the length of the pipe, over n. Unlike for all waves, we still have this equation. Lambda is equal to speed of the wave over its frequency. Now remember, the speed of the wave is the same no matter what the harmonic here is, because the speed of the wave depends only on the medium. So in here, the only things that change are the wavelength and the frequency. One last note, just to make sure, what we are looking at here is the pressure representation for it. Actually, it's supposed to say pipe open at both ends here. I'm sorry about that. Now, here we have pressure nodes. If I drew the displacement, it would be at the open ends, it would be displacement antinodes.